So thanks everyone for coming to this talk about Netty, which is the IO framework that propels demo. So I'm Stéphane LANDELLE. I'm the creator and the CTO of a load testing tool which is named Gatling. I'm an occasional minor committer on Netty. More often I kind of report bugs and ask some people to fix them. But that's a technology that I really love, so I wanted to spread the love. Just a few words about Gatling. So Gatling is a load testing solution, and you can use it to write load testing tests with either code, Java, Kotlin, Scala. Also use a no-code web interface on our cloud platform. If you're interested in it, we have a booth over there, so you can feel free to drop by. And so at Gatling, we really love Netty. We use it actually everywhere. Gatling itself, for its HTTP support, is implemented on top of Netty. And we also use it for the other bricks that we've used to build our SaaS product. So both we're using it through some web frameworks, and also you'll use it directly to implement some custom components, optimized ones such as an API gateway. So here's today's agenda. First, we are going to have a quick introduction about what Netty is. Then we are going to have a look at how IO works focused on Linux and how these APIs translate onto Java. We're going to have a look at the Netty API and then focus on some cool features and very nice and tricky and very hardcore engineering things that Netty has done over the years to make it super fast. And we'll have a conclusion about Netty's future. So first, what is Netty? So Netty is definitely the most popular for network library for the Java ecosystem. It's a low-level API, honestly, but it's actually used everywhere. It's used in most of the web frameworks that you're going to use as Java developers. So, for example, Vertex, Micronaut, Armeria. And also it's used to propel lots of different platforms, in particular most of the services at Apple. Also, if you play with Minecraft, the servers are implemented on top of Netty. And also it's used also by lots of different softwares from databases such as Cassandra. Gatling, also it's used in the Java SDK for AWS if you're using the async API in the version 2. So it's really everywhere. And so this is a library that was originally created by Mr. Tristan Lee, who has a talk in a few hours this afternoon. I recommend that you go and watch it and watch the great work he's doing with Armeria, the web framework Armeria. And currently, the project is being led by Norman Maurer from Apple. So what makes Netty so popular? The first thing is that over the years, it has brought incredible innovation and brought new features faster than the Java library itself. So, for example, it was able to support HTTP2 and TLS 1.3 faster than these features were available in Java. And also, they made them available for all Java versions, where those new features were not necessarily immediately or never backported. Typically, Netty, the Netty Java baseline for Netty is currently Java 6. So all those features are available for Java 6 users. It has, honestly, super great performance. The engineers, the core committers on Netty have really went to incredible extents to bring awesome performance in this framework. We'll cover this a bit later. And it has a good design. It's easier to use than the Java APIs, honestly. And also, it's very easy to extend this way, so it's very easy to implement your own protocol. So now let's have a look at how I/O work on Linux and how this translates in Java. So on Linux, the primitive that you want to use to do networking is the socket API. On the server side, you're going to open a socket, then you're going to bind on a listening port and start listening. And then you're going to call accept, so that you're going to block until there's some client that requests to open a socket. And then you'll get the file descriptor from the client of the client socket, where you'll be able to read and write from. On the client side, it's a bit different because you're not listening to a listening port. Instead, you're going to connect onto a remote address, and then same thing, you'll be able to read and write on the client socket. This translates exactly one-to-one on the Java socket API. Very similar. If you want to implement a TCP server, you're going to create a TCP server socket, the bind and on a given port and start listening, and then you're going to have a loop where you're going to block on accept that will be unblocked and return a new client socket when there's some request from opening a socket from a client, and then you'll be able to use the input stream to read from and the output stream to write into. The problem with this API is that it's blocking, okay? Input streams and output streams. So it means that what you had to do before, spoiler, you had to hand over each new socket to a dedicated native thread. And so you could achieve concurrency. And of course, this doesn't scale because native threads are very expensive. They cost lots of memory, and they trigger lots of context switching. If you want to spawn hundreds or thousands of concurrent connections and hence threads. Spoiler, this socket API was rewritten for Java, maybe 19, something like this. And actually, when it's being called from virtual threads, it falls back to actually performing non-blocking IOs underneath. So it's way more efficient, and you no longer suffer from this native threads high usage. But then, for a very long time, there has been better APIs in the Linux kernel to perform network, and the one that's being used all over the place now is EPoll. So EPoll is a different API, it's stateful, and it's event-based. So just like before with the socket API, we're going to, for a server, we're going to open the server socket, going to bind on a port and start listening, but then what we're going to do is that we're going to create an EPoll instance. And we're going to register the server socket with this EPoll instance. So it means that the EPoll instance is going to maintain a list of sockets of interest, and also you'll be providing, optionally, the list of events that you're interested in for all the those different sockets. And then you're going to loop, and on each loop iteration, you're going to call EPoll wait. EPoll wait is going to block until there's some work available. And what actually the kernel does is that it's going to every time there's work available or events that happen on your sockets, the EPoll instance is going to be notified and will update what's called the ready list. So so it will update in the background a list of available work. And this way, when you call EPoll wait, directly, if there's work available, you'll be notified. You'll return the list of available work, which is called the ready list, in constant time. You don't have to wait to scan all the registered file descriptors for each state. And so inside the loop, then, we are going to check for each event if this is either the server socket being requested for accepting a new connection, In this case, we're going to register against the EPoll, the client socket, and say that here we're interested in, for example, reading IOs. Otherwise, well, it means that we have some read events available, so we're going to read from the socket. And so this mechanism scales. And if you have a look at the Java and IO API that was introduced in Java 4, this is exactly what happens. It's really, the concept is really, the API is mapped almost one-to-one. So here we're going to open a server socket channel, so a new API from an IO. We're going to bind on the listening port, and then we're going to open a selector, and selector is actually the wrapper, a wrapper on top of EPoll. And then we're going to register on the selector the server socket and say that for this socket we're interested in accept events. And then we're going to have our loop where we're going to call the select, which is the wrapper on top of EPoll wait. And for each selected keys, meaning each entry in our ready list, we're going to check, oh, is this an accept event? In this case, we're going to accept the socket and create a client socket that we're going to register on our selector and register it for read events. Otherwise, if it's a read event that's available, we're going to get the client socket and read from it. And here, we're writing back on the socket. So basically, we're implementing an echo server. In Java 7, there was a new API introduced, which is an IO2. And basically, it's a very similar API, just that it has a more asynchronous vibe, where either it can return futures, or you can also pass listeners, which are completion handlers. And also, it has built-in support for timeouts. But regarding the network sockets, not really anything new here. It's more that this API introduced a different set of features for reading and writing in an asynchronous way on files, which real files, not network sockets, that EPoll doesn't support. So now let's have a look at Netty and how its API works. So here is an example. So what you're going, the core object that you work on when you want to create a client or a server is the bootstrap. And you're going to pass some different object to this. I'll explain them a bit later. So we are going to pass some groups, some event loop groups, configure the type of channels that we're interested in, and then configure how we want to handle the IO events that will come from the underlying socket and how we can write them back onto the socket. So first, the event loop groups and the event loops. So obviously, as the name states, an event loop group is a group of event loops. Event loops are, so first they wrap a Netty thread, and they have two different responsibilities. The first one is to interact with your IO implementation, so typically an IO, but also possibly other ones. And the other one is to be the task processor that will process your IO events with your own logic. How you want to process the bytes that you read from the sockets, and how you want to generate new bytes that you want to write on the socket. For server, you can see that we can pass two different groups of event loops. So basically two different pull threads too. One for the parent socket, so typically we would just pass one single event loop, and a group for the child sockets, where you would pass multiple ones. The second thing is abstraction that's interesting is the channel. Channel is basically the wrapper on top of your actual network socket. So Netty has support for TCP, for UDP, for Unix domain sockets. Unix domain sockets are kind of sockets that can be used for inter-process communication. Like if you have two processes that live on the same machine and you want to make them to communicate with each other. For example, it can be an application and its database that sits on the same machine. It can be multiple Kubernetes nodes, pods that live on the same node. And this kind of socket is faster than using the loopback localhost. Here on the Bootstrap, when calling channel, actually we're not passing a channel instance, we're actually passing a factory for channels. And when we're passing a class, actually, Netty is going to use reflection to create new channel instances. The next thing is abstraction is the channel pipeline and the channel handlers. So channel pipelines are basically, well, chains of channel handlers. And channel handlers are intercepting filters that will possibly filter inbound and or outbound events. So really, if you have some work available coming from the socket, then the work is going to be handed over to the first inbound handler that might transform something and pass a new object to the next inbound handler in the pipeline. And then at some point you might want to write back on the channel, and then it will process through all the available channel outbound handler, possibly being modified to ultimately result to writing bytes onto the channel. So channel inbound handlers, so they are the handlers that handle inbound events. The main method that they need to implement is channel read. So basically, they consume inbound messages. These would be typically used to implement decoders, like you receive some bytes and you want to convert them into a different object. And also, it will be used to implement your application handler that you would put at the tail of your channel pipeline. It will be the last element where you would implement your business logic. And so regarding outbound handlers, the handlers that process outbound events that go from your logic, your application layer, to the socket back, typically this would be used to implement encoders. So for example, I would say transform some Java objects into some protocol buffer bytes. Netty comes with lots of built-in channel handlers. It has support for codecs for HTTP1, HTTP2, handler for TLS, lots of different handlers that you can use and combine for your needs. And this is really where Netty's design shines, is that really you have typically would have one handler per concern. And then you can really do composition and assemble them the way you want, pick the one that you need for your use case, and assemble them into a channel pipeline. So here's a full example, almost full example of how you would implement an NIO-based HTTP1 server. So we're going to create a server bootstrap. We're going to pass two different groups of event loops. One with just one size for listening on the parent socket that's bind on the listening ports. And another one for processing the I/O events on the child sockets. And here the default size is twice the number of cores. Then we're going to configure the type of channel that you want to use. So here we're going to use NIO server socket channel. So this means that we're going to use NIO, compatible with the event loop group that we've configured. And we're going to use socket channel, so TCP. Because HTTP is built on top of TCP. And then we're going to pass the channel handler that we want to use. So the API lets you just pass one single handler. So here it's actually a trick. When you want to configure multiple handlers, you're passing a special handler that will set up other handlers and then remove itself. So first, the first handler in the pipeline would be the one in charge of SSL, of TLS. Then the one in charge of decoding bytes into HTTP request. Then the one in charge of turning back HTTP responses into bytes. And then finally, our application logic. So it's clear on this schema. So you see all the encrypted bytes coming from the NIO channel being handed to the SSL handler, which handles both inbound and outbound events. The SSL handler will then pass the decrypted bytes to the next inbound handler in the pipeline, which is the HTTP decoder. It will pass the bytes and build some HTTP request objects, hand it over to the application layer. And the application layer, based on the HTTP request, will ultimately generate an HTTP response back that will be processed on the other way, passed to the first outbound handler, which is the HTTP encoder that will serialize the HTTP response into bytes. And then the SSL handler that would encrypt those bytes. And then we would reach the head, we are back to the head of the pipeline. And those bytes then are being passed to the channel so that they can be written on the socket. So this was the way that you would handle events when you're inside the channel pipeline. But for some events or in some situation, you want different API, typically futures. For example, because you want to deal with events where you don't have a channel pipeline. For example, connection errors. You're on the client side, you want to open a new socket, and you get a connection refused. And you can get notified of this error because you don't have a channel, so you don't have a channel pipeline, so your handlers in a channel pipeline won't get notified. So in this case, for handling this case, Netty provides a future API. The current production version of Netty still supports Java 6, so it doesn't have it cannot use completion stage and completable future. So instead, it had to implement its own future API, just like Guava had to. And in particular, so this API lets you register listeners that would be invoked on completion. And also, it kind of splits the API between futures and promises. So the future is the place where you get notified of the completion, and promise is the interface that you would use to complete it, to register the final the outcome. This is a success, or this is a failure. Now let's have a look at all the the main tricks that Netty has implemented over the years to achieve great performance. The first one is the threading model in Netty. So the threading model is based on the event loops. So remember, and event loops are actually passed as a group, which is an event loop group. Every time your transport tries to create a channel, creates a channel, it's going to pick an event loop from the event loop group and register this event loop with the channel. And then the event loop will process the events for this channel for the whole channel duration. By default, you can register, deregister, and register to a different one. But basically, that's it. This has two consequences. The first one is that all the events, inbound events and outbound events on a given channel will always be processed from the same event loop. Consequence, you don't need to implement any synchronization in your channel handlers, because all the events will always be handled by the same thread and will happen sequentially, not concurrently. So it makes way easier to implement final state machines. Typically, I want to write something, but there's also a scheduled timeout. So which one are going to trigger? If you're in a concurrent world, it's going to be super complicated. Here, everything is on the same event loop. Second consequence is that the relationship between channels and event loops is a many-to-one. So one channel is always associated to one single event loop, but one event loop can process multiple channels. Important consequence, it means that you must absolutely avoid blocking inside your handlers, your custom handlers. Because if you do that, you're not only going to block the current channel, but also all the other channels that have been registered with the same event loop. So if you need to perform blocking things or long computations on some I/O events, you should better offload them to a dedicated pull thread. The second thing is a nice trick with Netty is its memory model. So let's go back to NIO. When you want to deal with memory with NIO, meaning that the bytes that you want to write on a socket or you want to read from a socket, you'll have to use the byte buffer API. It's a bit of a challenging API, kind of surprising, in particular because of its flip method. You need to call the flip method so that you can properly switch from writing to reading and writing back, etc. If you forget to do that, the actual internal indexes will be off compared to what you're expecting, and you'll get errors or unexpected results. And I'm pretty sure that everyone who's ever used the NIO API at some point has completely forgotten to somewhere call the flip and get some weird errors and spend a lot of time trying to figure out where he forgot to call flip. Byte buffer actually has two different kinds. The first one is heap byte buffers. Those are backed by a byte array, so in the standard heap object. And the other one is direct byte buffer, and here it's backed by off-heap memory. The advantage of heap byte buffers is that, well, they are easy to understand for Java developers who are very used to the garbage collector. Everything lives in the heap, and this memory gets easily garbage collected by the by the GC. Two problems. The first one is that you can hand over heap objects to system calls, so writing on the socket. So if you're using heap byte buffers, at some point, for example, NIO will have to copy them into an off-heap array so that it can execute the IO system calls. So lots of garbage being generated. The other thing is that when you are allocating an array in Java, as per Java specification, the JVM will memset this array with zeros, supposedly for security reasons, debatable. But so it means that you will have an extra work of using bandwidth between the CPU and the RAM to do the memset. On the contrary, the direct byte buffer is compatible with system calls, no extra copy. But the thing here is that, well, it's off-heap allocation, so it's more expensive to allocate. And then it's way more expensive to deallocate. Why is that so? Well, because in Java, the standard mechanism for freeing memory is the garbage collector that was originally intended for handling heap memory, not off-heap memory. So it has to go with some tricks and using references and using cleaners to free the byte buffers. And also, one other thing is that if you get when you hit an allocation failure, because, for example, your memory is too fragmented or the GC hasn't connected the reference yet, you will go through the NIO will trigger a garbage collector. But this method that will trigger the garbage collector is static synchronize. So it means that you're going to have a full stop the world for all your direct byte buffers allocations during this garbage collection. So it's not super performant. So in order to work this around, Netty came with the following solution. So first, it came up with its own byte array, byte API, which is bytebuf. In my opinion, it's sounder than the NIO one. First, the API is easier to use when reading and writing. You don't need to call flip and forget to call flip. And also, it can grow. The byte buffer cannot grow. They have a set capacity. While the bytebuf can regrow if you keep on writing. And if you do that, actually, well, still beware, because it means that you'll generate more allocations and some copies underneath. Allocations, well, depends. The second thing is that those byte buffs can be pooled. And this is something unexpected for Java developers. Because if it means that you have a pool, it means that you need a way to give back the objects to the pool. How can you do that? Because we don't want to use the garbage collector to do that. So we need a different mechanism, and the mechanism that's being used is a reference counting. Every time you want to retain ownership on a byte buff so that it doesn't get offered back to the pool, you will have to call retain, and this will increment an internal counter. Otherwise, once you're done with it, you're going to call release. This is going to decrement the internal counter, and when it reaches 0, the underlying memory will be offered back to the pool. Netty has a tool named the leak detector that helps you detect if you're not properly calling retain or releasing memory. It's pretty optimized. It does some sampling, and you can change the level. But yeah, I know that for Java developers, this gives a C vibe where it feels like you're doing memmalloc and memfree again. But well, this comes with advantages, and it's not that complicated actually. So now, how is this memory pool implemented? Netty has this pooled byte buff allocator, sorry, and it's heavily inspired from gmalloc. And now it has some features from gmalloc 4. So gmalloc, it's an allocator invented by Jason Evans, hence the name, gmalloc. And it was originally implemented for FreeBSD. And for a very long time, it's been the default allocator, malloc allocator in FreeBSD. The goals, when it was invented, were mainly have a proper scalability on multi-core architectures, and also have less fragmentation. So avoid having lots of unused memory all over the place that is being unused, but that you cannot use because it's too fragmented to be able to be used for allocating new objects. And actually, it's used in lots of different technologies, including Rust. This is the allocator in Rust. And so Netty, Netty couldn't directly use the gmalloc native library and have some JNI binding because the performance were not that great. So what they did actually is that they re-implemented something similar directly in Java. It's honestly very complicated, lots of research in there, but here is a simple way to understand the mechanism. So the first thing is that it relies on thread local caches. When you have some thread that wants to do some allocation and actually get some data from the memory pool, first it will hit a thread local cache, where there's possibly some memory available. If not, it's going to request the data from an arena, which is basically an allocator, and it has notions of pages and runs, etc., and chunks. But what's interesting to understand here is that the underlying memory is sharded into blocks and grouped by size classes. It means that there are, for example, some memory that would be available for small buffers up to 8 bytes, then from a different range, then from a different range. So when you want to allocate a given length of memory, the algorithm will know which size class this length belongs to, and will know where to look from in constant time. Then, also one cool feature is the native EPoll transport. There's also one for KQ. KQ is the equivalent of EPoll, but for FreeBSD and macOS. The Netty core developers figured out that the NIO could be optimized because it generates lots of garbage collections, and it has The way it uses TCP also could be optimized. And also sometimes they might want to be able to get TCP features that are not available, not exposed, or not exposed yet on NIO. So what they actually did is that they re-implemented, basically they re-implemented NIO. So they have some native code that's being wrapped with some JNI bindings. And from our experiments at Gatling, you can get something like a, depending on your use case, but a typical, at least a 10% boost. Another thing, also interesting thing, also is Netty TC native. So Netty TC native actually, so it was, it's a way to replace the SSL engine that's available in the JVM. And instead plug OpenSSL or one of its alternatives. This is something that was originally born from Tomcat, hence the TC. It was forked by Twitter to make it usable from Netty, and then Twitter donated it upstream to the Netty projects. What's interesting here is that it generates a bit less allocations. Some Cypher implementations are faster. And also some features are available sooner than available in the JVM. If you're not familiar, for example, with Boring SSL, so Boring SSL is it was born as a fork from OpenSSL from Google, and because Google wanted to get rid from all the legacy stuff that's still in OpenSSL and that cannot be removed from compatibility reason. And they were, we don't care about this compatibility, we just want to clean this up and focus on what's being used nowadays so that we can have an SSL engine for Chromium. So Boring SSL is the SSL engine for Chromium. It has a big warning, use at your own risk, we might break APIs, etc. It's being used for Chromium, period. But actually lots of people are using it because actually it's pretty stable. In particular, for example, it's being used at Cloudflare. Everything HTTPS at Cloudflare is based on Boring SSL. This also lets Netty benefit from new ciphers and new features like TLS 1.3 faster than the JVM and also helps backport things faster than the JVM usually does. On the older JVM version, I mean. One interesting thing too is the async name resolver. So this is for when you have to deal with DNS resolutions. The name resolver that's available in Java by default is inet address.getByName or getAllByName, and it's a blocking API. But remember, because of Netty architecture, we don't want to block. For example, if from an event loop you need to perform a DNS resolution because you want to open a connection to a remote host. So we don't want to block. We need something else than this blocking API. The second thing is that it uses an internal cache for caching the DNS records, and this cache doesn't respect the TTL that's set in the DNS records. It uses its own timeout, which is 30 seconds by default. So this can make things tricky when you're dealing with lots of DNS changes. For example, if you have some auto-scanning where you're adding new servers and new addresses for your host name. Also, if you're dealing with a Kubernetes cluster and you're moving instances around. And because you expect to respect the TTL of your DNS records, and actually the JVM doesn't. So instead, Netty implemented its own asynchronous name resolver based on its own standard UDP support. And finally, let's talk about the future of Netty. Innovation keeps on going in Netty. There's some nice, interesting work for supporting Quick and HTTP 3. So what is Quick? So Quick was born from Google because they wanted to fix some flows in TCP regarding Naggle, regarding flow control, basically. For example, also fixed like head of blocking. For example, think that you're implementing a video streaming server and you're implementing it on top of TCP. And so the server is sending some frame, but one of the TCP chunk gets lost. And in this case, all the other frames cannot be sent and received from the client until the lost chunk gets retransmitted and properly received. This is not what you want to do with real time. You just want to say, okay, never mind, let's drop this frame and just give me the next one. And this is not possible with TCP. And then, so the question was, should we implement TCP2? But this wouldn't work because of what's called protocol ossification. Basically, there are so many network devices deployed all over the world that it's completely realistic to think that we'll be able to update them to support TCP2. Just think about what happens with IPv4 versus IPv6. So instead, they decided to re-implement the TCP features they want to keep on top of UDP. And so this way, you keep on using a very standard protocol that's supported by all the network devices all over the world, but you would implement all the logic that's in TCP, not into the kernel, but as software in the user space. And software is way easier to update than network devices. And so HTTP3, it's basically HTTP2 running on top of Quick instead of running on top of TCP. And also it brings some interesting features, like, for example, connection migration. Connection migration would help you when not losing your connection. For example, if you're on your mobile and you're switching from your Wi-Fi to 4G. And how does Netty do that? Actually, it's riding on top of the work of someone else. Cloudflare is implementing, it's developing a quick implementation named Quiche. It's developed in Rust. And so Netty is developing some JNI bindings on top of Quiche. Another interesting incubating project is the support for IOU-ring. So IOU-ring is a new network interface, just like EPoll is one, that's been introduced in kernel 5.1, and that's been updated ever since. Originally, it was developed for files, but then it was extended to support network sockets. It's supposed to be super fast for some use cases. Myself, I haven't been able to reproduce it to achieve super great performance as great as EPoll yet, but keep on investigating. The thing is that the Google, for example, the Google bug bounty has been filled with exploits against IOU-ring. So I'm not sure it should be considered production ready at this point. And I know that Google has disabled it from Chrome OS. There's some ongoing work. There's been some ongoing work for years on Netty 5. So this would be the next major version of Netty. One of the goals is to drop lots of legacy stuff, like support for blocking transports, remove some technical debt, also increase the Java baseline from 6 to 8. Well, Netty is pretty conservative on that. And don't really need the super new features from then. Java 8 would be mostly interesting for using method handles to replace reflection in the few places that reflection is being used. It's also the occasion to clean up some API. So for example, the event loop. I mentioned that the event loop had two different responsibilities, one for handling IOs and communicating with the IO implementation, and the other one being the processor for the handlers. It will be split into two. But sadly, there's lots of work still to do, and the project is still it's a bit late, and I don't think there's any time arrival available. And finally, there's a fun question that's been popping for several months, which is what about virtual threads? Is Netty going to be implemented on top of virtual threads? Is Netty going to become obsolete now that virtual threads are out and that blocking IOs have been rewritten to support virtual threads? The answer is no. Not at this, or at least not at this time. So first thing, Netty is very, very unlikely to be ever rewritten with virtual threads because of its use of thread locals. In particular, I mentioned the usage of thread local for the thread local caches for the allocator, the pooled allocator. The second thing is that Netty doesn't actually need it. I mean, when you're using virtual threads with the socket API and that magically things are more efficient and scale and properly scale, actually what the JVM does is that it turns your socket code, API code, into NIO code. It's NIO that's being executed underneath with some global threads in charge of handling the read and the write, and notifying the virtual threads. You could perfectly do the same thing from your virtual threads to use Netty. So there's no really compelling reason to switch from implementing on top of virtual thread. You can use Netty from your virtual threads, just like you have to call to properly suspend and resume. What might be interesting is that it will bring new competitors and new innovation about IO frameworks on the JVM. So, for example, there's the Evident project from Oracle that has an IMA project. Well, it's currently being implemented out of Netty, and they want to replace Netty with virtual threads and native Java IOs. So thanks a lot for coming to this talk. If you have some questions, feel free to shoot. If you have some questions regarding this talk or about Gatling, feel free to drop by to a booth. And again, you should consider coming to Tristan's talk this afternoon. Thank you.